Thanks, Suba. Thanks, Jack. Thanks everybody for coming. I'm Sandy. I work at Cloudera on the data science team. I think I have a slide up still. Yeah. I would do data science at Cloudera. Before that, I sort of led the inclusion of Spark into CDH, Cloudera's platform. Before that, I was working on MapReduce and Yarn. I'm a committer and PMC member on the Hadoop project. I also recently authored Advanced Analytics with Spark, which sort of teaches about Spark through a bunch of real-world data science use cases. One thing before we go, I'd love you to interrupt me at any point, ask me questions. If you haven't heard of Spark, you could say that now. We could explain it and stuff. Yeah, I think that's all. So a coworker sent me this exception recently that he got. I don't know if you can see it from back there, but it has this cryo exception, and there's like this IWC character that comes up with all these dollar signs and anon fun. Sometimes thinking there should be a Tumblr for the kind of things that you see here. But this is one of the possible things that when you try to use this distributed system, you are immediately confronted with. There's a quick poll before we keep going. Who here has heard of Spark? Just raise your hand. Cool. Who here has written a Spark job? Who here has gotten an exception from a Spark job? Okay, cool. Anyone that has written a Spark job that hasn't gotten an exception? Well, you guys don't need this talk. You already know everything. So I like to think of exceptions sort of like manholes. They're always there, like lying around while you're walking around. You usually don't think about them, but sometimes you're walking near a manhole and it explodes, and it's really bad when that happens. And while it's really bad, a manhole is also this sort of nice thing that allows you to this sort of nice thing that allows you to go deeper in and examine what's happening underground. So similarly to manholes, exceptions allow us to figure out what's going on inside of Spark. This talk is going to be less if you see this, do this, change this configuration option, as much as like if you see this, here's the underlying reason why you're deeply screwed. Any questions before we get started? Cool. So here's our first beautiful exception. The punchline of this, to sort of cut the suspense, is that if you get this, it's probably your fault. It's not Spark's fault. But how are you supposed to figure that out? What are all these words that are being said here? What the hell is going on? You try to run a job, and suddenly this happens. So let's zoom in a tiny bit, cut out some of that stuff. There's three kind of interesting words here. When you read the Spark API docs, when you try to actually write Scala code or Python code or whatever to make Spark do things, you think in terms of actions, in terms of transformations, in terms of group by key, map, reduce by key, whatever. Suddenly you try to run your beautiful piece of code, and you get these three words that have not really been talked about to you before. Job, stage, and task. So what are these things, and what do they have to do with your misery when you try to run your Spark job? Let's start with job. So this is maybe one of the simplest Spark programs that you could imagine writing. It basically takes a text file and counts all the words that start with banana. We have two transformations here. So we're saying Spark context read this text file as a transformation. We're saying file.filter, which is also a transformation. It's going to take all the records and cut out everything that does not start with the word banana. And then lastly, we have this final operation count, which is not a transformation. Count is what Spark calls an action. So before we had called this count thing, we're basically building up a plan of things that need to happen. We call text file, it returns an RDD object. And that's sort of a plan for if we ever want to use this, here's where we would get its contents. filter says, if we ever want to use this, here's the parent RDD that has these contents, and here's this operation that we want to apply to each row in that parent RDD. Finally, we run count, which is an action, and now Spark needs to get its act together. Instead of just a plan, it needs to run some stuff on the cluster. So whenever you run an action, such as count, such as reduce, is different than reduce by key, or save as Hadoop file, something like that, Spark launches a single job on your behalf. So one action, one job. A job is composed of some smaller components. Inside a job is a set of stages, and in each stage is a set of tasks. Every task in the same stage is going to execute the same piece of code, but on a different partition of the data. Between two different stages, tasks will be executing different code, let's say farther along in the pipeline you're trying to execute. What the heck is a stage, and how do we decide where one stage starts, one stage ends? Why is this concept useful inside of Spark jobs? To try to make this sort of concrete, let's examine a slightly complicated flow of Spark operators that we might want to turn into some sort of production application. First of all, we have this text file chained with a map chained with a filter. So we're taking a file, we're transforming each record, and then we're filtering out some set of the records. Any questions so far while we're going on? Great. At the same time, so we built up this first RDD. At the same time, we're going to build up this second RDD, RDD2, which we have this similar kind of linear structure of things going on. We're reading some Hadoop file, we're grouping all the records by key, and then we're applying a map function to each group that will probably compute some aggregate statistics, something like that. And then keep bearing with me. Last of all, we have these two existing RDDs, and we're going to join them together and apply some sort of final map transformation to each record, which returns us RDD3. So again, this whole time, we've been building up a plan. We haven't actually executed anything on the cluster. So what happens when we want to run a job or execute an action that references RDD3? Spark sees RDD3.collect, which is going to take all of its contents, bring them back to the driver process, maybe for some local analysis. And it says, okay, what are all the different operators that are required to produce this RDD? It'll return this whole big thing. This is basically the things we were looking at before, smushed together into one large DAG, one large distributed directed acyclic graph. So this is an operator DAG, and what we'd like to do is turn this into a somewhat condensed stage DAG. The sort of relevant thing worth knowing about from a Spark perspective, from if you were inside the head of the Spark optimizer, is that these transformations over here, they're all element-wise. So assuming you have your data partitioned on your cluster in some sort of particular way, to execute this map and then to execute this filter after it, you don't need to move the data around at all, right? The only thing that the output of this filter transformation depends on is an output of a single record in its parent RDD, in its parent operation. So you have what's sort of called a narrow dependency. On the other hand, if you have something like group by key, any single output record in group by key could depend on the contents of every single partition in the entire data set. So when you run an operation like group by key, and join is also an example of this kind of operation, where the output can depend on inputs that are distributed all the way across the cluster, you have to have what's called a stage boundary to execute a shuffle operation. If you're familiar with MapReduce, this shuffle operation is sort of what happens in between the map and reduce stage. And Spark sort of generalizes it, extends it to arbitrary DAGs of operators.
So suddenly, You mentioned the Hadoop file thing. Is it beneficial to do, with a Parquet file to get better performance in the good key and then load it from that perspective? Or is, I mean, I'm sure it applies to both, let's say, in a Parquet, but performance-wise.
And so the question was, is Parquet more performant than text files, or?
No, is it, I mean, yeah, it's the primary that will be there, but I mean, I know it's more performant, but in terms of this particular aspect of things, we do good by key.
Mm-hmm.
We definitely see better performance on a power on a Parquet versus a text file.
I mean, so the question was, does the performance of this group by key, is that affected by whether you're using a text file as input or a Parquet file as input? It shouldn't be, because basically in both situations you're reading records into some sort of internal memory representation. So what you're actually grouping isn't like the raw Parquet bytes, but it's some like Java objects that Spark has deserialized. If you're using a text file, that'll probably dominate the performance more than using a Parquet file, because Parquet is more efficient. But it shouldn't affect this shuffle.
Is there a difference in performance between Python, Java, and Scala as compared to this?
So the question was, is there a difference in performance between Python, Java, and Scala? Java and Scala should be totally the same. Python in general is much less performant. Sort of the main reason for that is anytime you do an operation that calls, let's say, a Python UDF, you have to take your data, serialize it, and send it over a pipe into the Python process for it to execute. You can't currently compile like arbitrary Python into like JVM bytecode and have it execute there. Any other questions before we keep going? Cool. So Spark takes this sort of bigger DAG of operators, and it compiles it down into this simplified DAG of stages. So each of these pink rectangles is a stage, and we have this stage follows this stage, and then finally the results of our final stage are computed by taking the results of these two input stages. So inside a stage, you have a set of tasks. As we talked about before, a stage is composed of tasks, each of which executes the exact same code, but on different subsets of the input data. So if we go back here, one of the tasks in this stage will be taking some subset of records in that presumably huge text file, applying a map transformation to each, applying a filter transformation to each, and then writing out data to the shuffle. While another task will be doing the same thing, but on a different subset of the records. Sometimes, if you do bad things, or Spark does bad things, a task will fail. As a fault-tolerant system, Spark is usually okay with this. So if it sees a task fail once, it'll basically try rerunning that task on a different node. Sometimes your task keeps failing, and at that point, Spark thinks, okay, maybe it's not the node's fault, maybe it's not like a transient networking issue, maybe it's actually a fault of the code in this task, or something fundamental about the way the job is configured. So when I think the default right now is 4, when 4 tasks fail in sequence, Spark says, okay, this task is never going to run. Because this task isn't going to run, this stage isn't going to run, and we'll basically fail the job. So if we look back to our original message, that's exactly what's happening. Job is aborted because one of the stages was aborted. Why did the stage fail? The stage failed because the task failed. It didn't fail once, it failed 4 times, which may be kind of hard to see from back there, sorry. Mercifully, it tells us what the exception that caused the most recent failure was. In this case, it's an arithmetic exception divided by 0, which isn't cool in most math systems. So the job has failed. Any questions about that before we go on to our next exception?
Question. What was the TID?
So the question is, what was the TID over here?
Yeah, what is that?
So that's the task ID. That's the it's the sixth task in the job.
Is that useful, or is it just like, can you actually use that to figure out which data caused the failure?
Yeah, so I mean it's useful. You can go in the web UI, see various statistics and metrics about that task. you might be able to find that that task is shuffling way more data, or something like that, dealing with way more data than other tasks. If there's skew, and that might be useful for helping you figure out why it was that task in particular that was failing. Yeah, good question. This is probably the most common exception that we see in Cloudera support tickets. When people are trying to get things up and running in production, often people will write a program on some small data, it'll work beautifully, then they'll try to use their 200 node cluster and run that same program on huge data, and they'll run into something like this. The really fun thing about this exception is that the ultimate underlying cause has nothing to do with what you were seeing here. This is just a total symptom. So to actually really figure out what's going on, we have to step way back and understand Spark architecture from a holistic perspective. We're going to be talking about Spark on Yarn here. I would say most of the Spark clusters that I interact with have this as their setup. For those of you familiar, Spark can also run on top of Mesos or its own standalone cluster manager. But we're going to focus on Spark on Yarn at this moment. So this is the sort of basic Spark architecture. Nothing too complicated. We have this driver process. That's the process that the user code is actually running in. I like to say it's sort of this Stalinist figure. It's a totalitarian authority. It decides everything that goes on in a cluster. And then it has these minions that are running all over the cluster. A minion is an executor. And these minions are in charge of basically hearing from the driver. The driver will say, "Can you please execute this? Can you run this task on this subset of the data?" And the executor will make that happen. Yarn has a somewhat similar but a little more convoluted architecture. It also has this Stalinist totalitarian figure, the resource manager, which decides everything about the cluster. And then it has these KGP agents on every node in the cluster, making sure that the resource manager's bidding is done and nobody gets out of line. So resource manager and node manager, those are both Yarn processes. Unlike Spark, the goal of Yarn is to run external processes. So it does these things that it calls containers. A container is just a process that's launched by Yarn. And so when you're running an application on Yarn, you have one special container known as the application master. The application master is special because it has the ability to request additional containers from the resource manager. And then you also have whatever additional containers the application wants to run. So how does Spark fit into this picture? Executors go inside containers. So they're a Java process that's started by Yarn. And they run tasks inside of them, which are not new processes, they're just threads. And then where does the driver go? Spark actually gives you two different options here. In Yarn cluster mode, the driver is the application master, so it runs inside of a Yarn container. In Yarn client mode, the driver runs on a node, an edge node on the cluster or on some other machine. And a special application master is there that's just responsible for requesting resources from Yarn. It's not doing any of the actual Spark job coordination, any of the like compiling operator graphs into stage graphs or anything like that. Yeah. So the question is, can I explain the performance benefits of client versus cluster? I'll explain sort of the general trade-off. The reason you want to do Yarn cluster mode, which is back here, you have the Spark driver running inside of a container, is that the application is fully managed by Spark. So if the client process goes away, the application can keep running. It also means that Yarn can restart the application if something goes wrong. The main annoying thing about running in cluster mode is if you want to have an interactive sort of experience, if you want to be running Spark Shell, then this is insufficient because you're not actually on the node with the container. So in that case, you'd want to run Yarn client mode. There shouldn't be huge performance differences between them. Yarn client mode can be a little bit faster to start up because it doesn't have to launch doesn't have to wait for the application master launch to start launching tasks. The other thing is you want to make sure that in Yarn client mode, your driver is on an edge node or something with a very tight networking capability with the rest of the cluster nodes, or you can end up with all sorts of bottlenecks there.
So when I'm firing off a cluster like this, where is my data initially, my files?
So the question was, if you are firing off a cluster like this, where is your data initially? Typically, your data is on the cluster, so it's stored in HDFS, and you would have an HDFS data node co-located with every node manager on every machine in the cluster. So when you schedule a job, Spark, in coordination with HDFS, are responsible for figuring out what data nodes you need to talk to in order to actually fetch what you need.
So typically, you would instantiate a cluster, and then the cluster will be live for a long period of time, and it will persist the data, and you just keep sending jobs. So it's not like you need a job done, so now you instantiate a cluster. And
yeah, so I think it depends. There's definitely models of running Spark that are that. In that case, you'd probably be hosting your data inside Amazon S3 or something like that. And there are APIs that allow Spark to fetch data from S3.
So is the question, is execution near the data?
Right.
Data locality, maybe?
Yeah, exactly. And that's basically up to you. There's big performance advantages of having, putting your data on HDFS and having the execution near the data. But the trade-off is that if you're only using the data very rarely, it might be that having a HDFS cluster all the time is too expensive.
If I understand right, the client actually, the first point of interaction is the resource manager, and resource manager is responsible for starting the application master and one of the containers in the node manager. So if that's the case, right, so this application master can be in any one of the node managers. So how does resource manager choose which one to choose among the node managers which are available in the cluster?
Yeah, so it basically picks a totally random one. There's like no, there's no real criteria for why it should pick, this guy versus that guy. Good question, though. Did you have a question?
No,
Okay.
It depends on if the Yarn's managing the resources across the cluster. It's going to create a container that has the most available resources, though, right? As opposed to like round robin or random.
Certainly. So it's not going to pick a node that's already saturated with other stuff. It'll be based on availability.
I might be jumping ahead a little bit, but is there a way to pause all the Java threads running everywhere to examine like stack of state of each node and kind of examine where everybody's at or something?
That would be really cool. But unfortunately, you can't do that.
Okay.
That'd be awesome.
How?
Did you someone else?
Just if you can send the command hold.
Yeah,
You
exactly.
wanna
Hold.
stop?
Pause. Just press the space bar. So if you run into that exception that we saw before and you're really desperate, you might start looking in application master logs, executor logs, resource manager logs. Eventually, you might get to the node manager logs. If you were to look inside the node manager logs, likely what you would find would be a message like this. So for those in the back, this says container, and it gives some sort of process ID and container ID. It's running beyond physical memory limits. Current usage is 2.1 GB of its limit of 2 GB, killing container. So summary, Yarn is seeing that the container is using more than it was allowed to, and it's shooting it in the head. Why would this happen? Why would anybody use more than they're allowed to, and why would Yarn be so merciless? So I think understanding this requires a sort of brief understanding of. So we've gone to the top. Now we're going into the nitty-gritty of these Spark and Yarn configuration properties. Understanding why this happens requires understanding some configuration properties. The sort of top level one on any particular node is this yarn.nodemanager.resource.memory MB. So this is the capacity of the node. For all the containers that are running on the node, it could be one, it could be a billion. The billion would be very, very large. The sum of all their memory usage has to fit inside of this number. So Spark has to figure out some number to communicate to Yarn that it wants to use for its executors. So it has this, it doesn't get to say, you know, I want to use all the memory and just track as I go. It has to say, I want this sort of allocation for a particular executor, and then Yarn will schedule it. And that's how Yarn avoids smushing things together and over allocation of resources. So if you ever mess around with Spark memory configurations, probably one that you touched is spark.executor.memory. If you use Spark submit, just -- executor memory. This is the size of the heap of the JVM process that is running the executor. So you know, for allocating all sorts of Java objects, this is as big as you can go. The sort of annoying thing is that when you run a JVM, there's the memory that's immediately claimed for the heap, but also sometimes the JVM will consume some memory off heap. If the JVM does string interning, it will do stuff off heap. If it's using certain compression libraries, it'll allocate direct byte buffers. If it's doing certain math operations, let's say using BLATs in direct byte buffers, that can do that. So there's this extra space that's used to basically pad the amount of memory that is requested from Yarn when you run a Spark container. But by default, it's I think now been boosted up to 10% of the Spark.executor.memory. But it can definitely happen that, you know, depending on your application, depending on what you're doing, you blow past that 10%. So in that case, the heap plus the extra memory is exceeding what Spark requested for its container. Yarn is periodically polling the usage of this process, and it sees it, and it kills it. So the solution in this case is basically to manually bump this property, manually bump spark.yarn.executor.memory overhead. Any questions about that?
You can't do that while it's executing, though, right? This
No,
is
you
not
gotta
on startup, right?
Exactly. Yeah, it's
So
an application-wide.
what do you use, like, as a general rule of thumb, like some general training? I mean, as your data set changes and your heap expands based on the serialization of objects in and out, based on, you know,
right. I mean, so
you know what I mean? Like, where do you?
It used to be more. So it used to be this was hard coded to 384 megabytes, and then as you increased your executor size, you had to scale it. Now it's an automatic 10%, which will generally scale, you know, as you increase cellular executors. So it's only if you sort of find out that your application is using way more off-heap memory than it.
That's 10% above the amount that you've asked to, like.
Exactly. So if this is, you know, 10, this would be 1.
Yeah.
And then it would ask for 11.
You can't do it just based on the percentage available memory
on the
container?
machine. No, it's, yeah, there's no ability for letting you do
So, I
that.
mean, as long as you ensure that your executor overhead plus every memory is less than the unknown manager or resource memory, you're good to go.
Exactly. Though, I mean, often it's useful to run multiple executors per node manager, so you have to sort of do a little more complex calculation.
This, you are talking about the stack memory, right?
I think the stack in Java might also go on the.
If it is stack, you can just say limited dashes, unlimited, and you get unlimited stack.
So it's not only the stack. You're right. I think that I'm not sure whether the stack runs off of the heap allocation in Java.
Stack, right?
But in addition to the stack, there's also, you can allocate direct byte buffers that aren't counted inside the Java heap memory.
If it is stack, then you can get over by just say in your dot dash RC or something.
If it's stack, you can limit that.
Then you
Well,
can
it still has to fit inside the yellow box though, right?
Yes,
Yeah.
you can go over that.
Right. I mean, so basically this property, these two properties together define the size of the yellow box.
So aside from like GC collect and stuff, is this where you might want to think about like what's an RDD trying to spill the disk and stuff like that, so you can free up some of the heap, or?
So the question was, is this the point where you want to think about spilling to disk when you're doing this? In general, Spark should sort of have other controls for doing that stuff. So no storage level when you're caching an RED should lead you to hit out-of-memory errors. If they do, that's a Spark bug. If you're doing like memory only, it'll just not cache the partition, so you'll have to recompute it each time. And if you're doing like memory and disk, then it'll automatically spill in those kind of situations.
So this memory overhead, I think you mentioned, but just to reconfirm, includes things mainly like this Fortran library or like JNI, any sort of JNI stuff goes in there, right?
Exactly.
Okay. And so how do we figure out whether it's the memory overhead that exceeded or the Spark execute or the Java side of things?
So whatever you set for the Spark executor memory, it's gonna immediately claim all of that. So if you set 5G, then even if you're not using that much heap space, that's gonna be claimed by Spark. So if you're going over, you know that it's because you don't have enough memory overhead space.
And and the log said that we just went over at some point, and so that it must be that left part.
Exactly.
Okay.
So the Spark executive memory, that's your XM, XN, your XMS?
Exactly.
Yeah, okay.
Yeah, they set it to the same just to be easy.
Cool.
So just to clarify, it doesn't mean that your RDD is exceeded the...
Exactly. It does not, crucially, it does not mean that your RDD has exceeded the size.
It's just that little piece.
Right. So Spark should handle that gracefully if your RDD exceeds the size.
So, and if you were actually running out of memory on the Java side, then you should probably get something else like out of memory exception or something like that.
Right. I mean, so if you are running out of memory on the Java side, so we'll cover some situations that can lead you to hit that in a couple of minutes. But usually it's either your fault or it's a Spark bug. Spark somehow isn't tracking memory in the way that it should, or it's doing it too fuzzily. Or your application is just newing a bunch of huge buffers.
Okay.
So, why do we get this? I don't have a really satisfying explanation for you. Basically, as an executor shuts down, there's some sort of complex set of Hadoop shutdown. The executor, this happens in situations with executors communicating with a data node. And so there's some sort of like last words of that communication code. Weird shutdown procedure, and it just spits out this file system closed exception.
The log files on Yarn versus the log files on Spark, but at least when the errors happen, they're different. So you don't see the same error messages on the Spark side when the Yarn cluster actually sprays.
Right. So Spark is sort of in charge of its own logging, and Yarn will just tell you that it shot down a container.
But you don't know why.
Yeah, in this exactly. Recently, so the situation's improved a little bit since we hit a lot of these exceptions. Now Spark will, when it finds out that a container died for this reason, it can go to, Yarn can tell it that a container died for exceeding memory limits. You don't actually have to go to the node manager log, it'll spit it out in your driver log, and you'll see this is what happened.
Is that in 1.3 or?
Yeah, it's in 1.3.
Okay.
Any questions? Okay, keep going. That's cool.
One question. So even if you're running in client mode, you'd still see it on your laptop, so to speak.
Right. So if you're running in client mode, you would see it on your laptop. If you're running in cluster mode, you would see it in the application master logs.
Okay.
Sometimes the problem isn't that your job is blowing up. Sometimes it's just going really, really, really slow, and this can be very unpleasant. Why do things run really, really slow? GC stalls are one of the biggest reasons. Because Spark runs inside of Java, it's great, it makes development really easy, but also there are lots of things you can do to end up in situations where the garbage collection time really dominates what's going on. So over here, this is the Spark web UI. For a particular stage, you can look at all the tasks that ran. Sort of relevant thing to notice here is for each of these tasks, each of them is taking 12 hours. And the time that that 12 hours that's spent in garbage collection is 9.59. So 9 hours of just cleaning stuff up and cleaning the heap. That's no good. You don't want that. Too much spilling. So we'll talk a little bit in more detail about how spilling works or what spilling means inside of Spark. But when you're executing some sort of shuffle operation, often you have more data that can fit in memory and you need to spill to disk. And if you do this, if you configure things wrong, incorrectly, you can end up spilling lots more stuff to disk than you really want to.
Just regarding perf, not so much for memory consumption, right? I mean,
Right, exactly. So you wouldn't necessarily hit out of memory errors if Spark is doing its thing right. So let's talk a little bit more about the situations in which Spark spills. We're going to be talking about less about caching and more about DAGs operators, more about Spark in action than at rest. Because even when you're not caching things, you end up having to use lots of memory when you're doing these sort of large distributed aggregation operations like group by key or join, etc. As we discussed before, whenever you have a stage boundary, you enact this kind of thing that's called a shuffle. A shuffle takes the output data from one stage, organizes it in such a way that the next stage can consume it, and transfers it across the network. In this case, every task from this stage is writing out shuffle data to disk. Then every task from this stage is coming up requesting the relevant shuffle data for itself, and the shuffle, the Spark internals are responsible for making sure that the disk format of the stuff that's written out is in a nice way so that these tasks can come and fetch it really easily. Over here, both of these stages are writing out shuffle data to disk, and then this single stage is fetching from both of the shuffle writers. This is maybe a better diagram of this. Most performance issues when you're running a job are in the shuffles. Shuffles are usually unavoidable because that's why you're using Spark, you're able to do these cool distributed operations, but shuffles are also the cause of most problems in Spark. When you're just doing an element-wise transformation on a bunch of records, that's not going to cause you a lot of problems. But when you're actually playing around with lots of memory, you're gonna hit stuff. So we're gonna focus a little bit on what we call the reduce side of the shuffle. This reduce terminology is a little bit weird for Spark. It's sort of a vestigial sort of holdover from the MapReduce days. When we think of a shuffle, we think of map tasks are the ones that are writing out the data, and reduce tasks are the ones that are consuming or fetching the data. So this is a sort of basic word count scenario. Each of the map tasks has a bunch of different words. We want to group together all the words that are the same and their counts inside the say local documents that the map tasks are processing. These three different tasks all have Apple showing up, and they send it over to this reduce task, and that reduce task is then going to take all those records and reduce them. What does it actually look like inside this reduce task when it's doing this sort of aggregation kind of thing? After the map paths have written out all of their data to disk, everything is nice and quiet, and then the reduce tasks come along and start issuing fetch requests on the map side. So if there's 2,000 map tasks, each reduce task is going to issue fetches for 2,000 blocks. And these blocks are basically going to stream in to into the reduce task and then slowly get processed.
Does shuffle and reduce mandate spilling to disk? Just so that
so the question was, does shuffle and reduce mandate spilling to disk? So whenever a shuffle is enacted, data is always written out to disk. This is different than, let's say, Impala does full in-memory shuffles, because it's trying to optimize for performance a little more. The spill to disk approach is how MapReduce does it, and that's also very nice for fault tolerance and reliability. You don't have to have all the tasks up at the same time, so you can complete the stage. It makes sort of scheduling and resource management much more fluid, because there's all this data at rest, and you come and get it when you need it. There is, on top of that, additional spilling that can sometimes happen, which is the spilling that we want to try to avoid. As blocks come in, they're thrown into this data structure that we call an external append-only map. It's external because it can spill. It's append-only because you never need to actually remove stuff from the map, and it's a map because it maps keys to values. So if we're doing a reduce by key, and let's say doing a basic word count kind of thing, each of our words is a key, and then next to a particular word, we want to have the count. So blocks will come in, and we want to sort of force it into this data structure. As blocks keep coming in, this expands. It takes up more and more memory. Spark closely tracks the amount of memory that it uses. And when it hits some sort of limit, when it goes past the amount of memory that Spark has allocated for that data structure, what needs to happen is that Spark needs to sort that data and spill that data. It sorts it so that if you have multiple spilled blocks over here, it's very easy to merge all the contents. You'll have key 1 and its values in this block, and then key 1 and its values in another block, and you want to be able to shove those together to get the final count for a particular word. So as data comes in, when it hits the limit, you take the existing data, spill it all to disk, and then keep filling up more data in memory until finally you've received all of your shuffle data, then merge all these on disk segments. That's sort of it's a bombard of information, but any questions about that before we?
So when the new data comes in, it will sort that and then it will bring back the one which is spilled to disk and again sort the whole thing and then push it back. So at some point, when the final spill, you'll have everything in a sorted order. Is that the way to do it?
Exactly. So if you're not doing any spilling, you don't necessarily need to do any sorting. But in situations where you do spill, then you do have to do the sort.
So a shuffle happens at an end of a stage, correct?
Mm-hmm. Or a boundary between two stages.
Right, and so there are a bunch of stages going on in parallel. So as one stage ends, it initiates its shuffle. So that it doesn't wait for all the stages to finish to start initiates shuffle, right?
Right. So I think maybe like you're thinking of tasks. So you have a bunch of tasks that are running concurrently as part of a single stage.
Yes.
And so yeah, there's no coordination that needs to happen between tasks within the same stage. They basically just all write out their data as they process it in the right format.
Right. Thank you for correcting my terms.
Can you tell what external appending map means? Like what do you mean by external appending?
Right. So the question was, what is external append-only map? What does that mean? So external append-only map is this data structure that's in charge of storing key value pairs as stuff comes in. We're using a map because it's used for these operations like reduce by key or group by key or aggregate by key. It means to do key value pairs. So it's a map. The reason that it's external is because it can be spilled to disk, external storage. And it's append only because there are optimizations inside of it that rely on the fact that you can never delete things or update things from the map. It's only adding new things.
So do these shuffles always happen at a point where you actually need to do some kind of sorting by key?
Yeah, so sorting by key or reducing by key or grouping by key. Whenever you're doing a sort of by key operation where you need to assemble all of the different elements from different partitions that correspond to the same key into a single partition, then you need to execute a shuffle.
So these sorts are never done unnecessarily. It's always required because of the nature of the operation.
Right, so you would never do a shuffle unnecessarily. It's always required because of the nature of the operation. This sorting isn't technically required. It's just the most efficient way to write out on-disk files so that they can be merged in an easy way.
Okay.
In theory, you could do some sort of complicated partitioning scheme, like
Repartition.
yeah. It's like there are like fancy ways you can do that. I know that Impala does something like this. It's maybe farther along the line for Spark. Other questions about that? So the problem with this basically is if you're shoving tons and tons of data through a particular task and you're shoving it through this data structure, you can hit both the issues that we were talking about before. You can hit garbage collection because when you have this external append-only map, you're holding a ton of Java objects. They're not the kind of Java objects that are that can stay in the young generation. If you're let's say allocating a Java object per record to process, put that in there, to process records, then you can immediately garbage collect that as soon as it's done. But if the size of this exceeds the size of the young generation, that's going to get moved into a older garbage collection pool, and then it becomes much more expensive and much more time-consuming to garbage collect that that object. So so when you have a ton of shuffle data going through one of these particular data structures, you can result in a lot of garbage collection. Also, you can end up doing a lot of spilling. So ideally, you would like to do zero spilling. If the data is small enough to fit in one of these data structures, you don't have to spill at all. But if it's too large, you do end up spilling. So how do you control this? How can you avoid garbage collection in this situation? How can you avoid spilling? There's basically this magical knob that Spark gives you, which is the parallelism argument of the shuffle. If you're familiar with MapReduce tuning, this is basically the equivalent of setting MapReduce.reduce.tasks, or whatever the configuration is. It controls the number of tasks on the stage that's on the reduce side, that's on the fetching side of the shuffle. So it doesn't tell you anything about the parallelism of the tasks that are writing out to that stage, but what this says is let's use 1,000 different tasks to be in charge of fetching all the data that exists there. So what you can do if you plan and do things right is you can make it so that each of the tasks is only processing a reasonable size subset of the data. And so if you're processing a reasonable size subset of the data, you don't end up holding as much stuff in memory, you don't end up having to spill on those kind of situations. Does that make sense why this works?
So the number of partitions, okay, we decide, okay, if we have 1,000 or 10,000 partitions, then reasonable size data. But what if we don't have that amount of resources available in our cluster? Then now, so then what, is it still reasonable to do that and just kind of swap the whole thing instead of having to garbage collect? Do we still win or not?
Great question. So the nice thing is it's not actually important how many resources that you have in your cluster, because Spark does this stuff where it writes all the map output data to disk. You don't have to run all of these tasks concurrently. So you can run, let's say, a wave, like let's say the highest number, you only have 250 cores on your cluster. So you can only run 250 tasks at once. It'll run a wave of 250 tasks, each of which will process their section of the data. Then it'll run a wave, like another wave of 250 tasks. So you don't actually have to be running all these tasks at the same time.
Okay, so it does not prevent spilling, but it will help us with garbage collection.
So it does prevent spilling. Nothing is going to stop Spark from writing out the map output data to disk in the first place. But when we talk about spilling in Spark, we're thinking about sort of the second level of spilling that happens when you try to fill out these enormous external append-only map data structures. And what this is basically saying is don't try to bite off more than you can chew with each task so that you need to spill again.
So the question I have is this: the reduce function has to be able to have support 1,000 operations. For example, if the reduce function has only 3 keys, it's not going to use 1,000. Maybe only 3.
Right. That's certainly true. So yeah, if you're doing reduce by key and you only have 3 keys, then you can't increase the number of partitions beyond 3 isn't going to do anything for you. You'll have empty tasks.
Yeah. So it's all dependent on how many.
Right.
How you write your reduce function first.
Right. Is there a question back there? Okay. Cool. So yeah, so you can run them in waves basically.
So we tried something like this. We have like this join was kind of skewed, and then can skewed join, and where basically we are left out of join, and we could potentially have a whole bunch of things that fall out. So in MapReduce we have the long reduce problem. So here what we're trying to do is we try to repartition it into smaller chunks so that it never it just takes a bite-sized piece. And
right.
I think we have got it to a point that it's kind of working. We can't really solve it totally. But do you think that's the right way to go with this, or?
Yeah, I mean, if you have inherent skew in your data, like a ton of records that are, attached to one particular key, this isn't really going to help you there. You have to be able to find some way to do extra partitioning within that key. The way Hive Spark does this, or the way it does sort of handles huge joins in general, is that instead of using the join, it uses this repartition and sort within partitions operation. So what that does is it basically is able to avoid holding a bunch of stuff in memory at the same time. It can sort of stream over the data in a better way.
It spins up a bunch more reducers then?
So no, so it would be the same number of reducers, and you would be processing the same amount of data per reducer, but you would have to hold less of that data in memory at a particular time. You wouldn't have to hold all of the values that correspond to a particular key in memory at the same time.
Oh, it has to sort. So how's it going to do that?
So it pushes that sorting down into the shuffle. So you're right. Somewhere in that,
Okay.
you end up using memory in that way, but it can be more efficient because it pushes that down.
So you just mentioned Hive Spark. Can you, I guess it's always still with
The status of Hive Spark. So I should know this. I think we just released CDH 5.4, as well as today. Spark 1.3 came out recently. Some version of you got to upgrade.
Yeah, exactly. That's right.
Sorry.
Okay.
I'm so sorry. But 5.4 includes Hive Spark, which is, I don't know if we call it production ready yet. We might call it.
It's beta.
It's beta. But we put a bunch of work in it. I would definitely suggest trying it out.
What are the factors we should consider? Because always having more partitions may not really help. There might be an optimal number, and what are the factors we should consider before we arrive at that?
Great question. So this is all dandy, but why not just set num partitions to like 2 billion each time to solve all our problems? I don't know why they didn't put that in the Spark code itself. So if you have too much parallelism, these are the sort of problems that you can run into. First of all, there's some overhead for each task, just starting it. You have to transfer some serialized chunk of bytes to an executor. The executor then needs to launch that, throw something on a thread pool, blah, blah, blah. When you have more parallelism and more partitions, you end up doing more fetches. So the total size of the data that you fetch is the same, but you're fetching it in smaller chunks, so that you end up doing a lot more random reads on disk. And then there's a bunch of state that needs to be tracked per task that makes it so so that you don't want to overload the driver with 2 billion different tasks. What's the best way to figure out the optimal number? One thing you could do is this. So this is this crazy formula that I came up with. The best way probably to understand it is to look up the blog post I wrote on this. It's like Spark Performance Tuning, Sandy, Part 2. So basically what you're trying to do here is you're trying to set it up so that the amount of data that goes into each shuffle, or into each reduce task is going to fit inside the amount that's allocated for that reduce task. So you can calculate both those quantities by looking at some configuration options, observing how much space your data takes up in memory, observing how much it takes up on disk. It's really ugly. It's kind of nice to know that it can be estimated a little bit. What I really recommend to people is just keep multiplying the number of partitions by 1.5. And at some point, it's going to stop increasing your performance. It'll probably flatten out before it actually decreases it. So at that point, you're good. Which is maybe not the most beautiful answer, but in practice, I think it works for most people. I think that is that's all. Yeah. So the last thing, whenever I finish this talk, is Spark bad? No, Spark is not bad. It's great. It's just distributed systems are really hard. It's trying to do a lot of stuff. It's still a fairly new project. Since I think the first time I gave this talk, we've improved it a lot. A lot of stability fixes have gone in. I'm currently trying to rewrite a bunch of the shuffle code, so these garbage collection problems and spilling problems are a lot smaller, and it's just getting better and better. So thanks a lot. So the question is, if I have a really big self-join, any distributed system is going to struggle. Do I have any suggestions? I mean, so the one, the biggest thing that affects shuffle performance is the number of partitions. I would play with that. The way you store the data and the in-memory representation matters a lot. So are you using data frames, or are you using?
I'm using S3, pointing to S3.
Mm-hmm. But so the actual like stuff that's getting shuffled, is that Java objects, or is it like Spark SQL rows?
It is pure string rows.
Mm-hmm. So I mean, one thing that's often hard to deal with, but to be aware of, is that strings take up a lot of memory in the JVM. There'll usually be some sort of prefix that's like a couple of bytes, and then it stores everything as Unicode, even if you have much more restricted character sets inside your actual data. So if you're using, let's say, unique IDs, and those could be integers, and you want to do a join there, converting the strings to integers could be really helpful. That kind of stuff. Generally, looking at your Java objects and trying to figure out how much space they take. Often you can optimize them in various different ways. And then turn on cryo if you're not doing that already. By default, Spark uses Java serialization for sending stuff, and that's really slow and cumbersome.
What are your thoughts on Tachyon?
The question is, what are my thoughts on Tachyon? I have sort of a lot of them. They're somewhat complicated. I think it's a pretty cool thing. I'm not 100% convinced that other components that are in the greater Hadoop ecosystem don't provide the most important parts of it. For those who aren't familiar, Tachyon is this project that also came out of the Berkeley Amp Lab, which is where Spark came out of. Tachyon provides the ability to do, it provides a file system that implements the Hadoop file system interface. You can write data there, and instead of that data being immediately persisted to disk, it goes into memory, and Tachyon will store all the relevant information that's needed to recompute that data in case that data, in case the in-memory copy is compromised. So this is nice for sort of two different things inside the in Sparkland. You can persist the results of a Spark job or a MapReduce job out to Tachyon, and then share in memory with other Spark jobs. So the sort of advantage there is you don't need to hit disk on the right side before another Spark job comes and reads that data. The other thing that Tachyon provides is a off-heap cache. So when you're doing RDD caching, when you say like RDD.persist, instead of storing it in big byte buffers inside the JVM, you can store it inside Tachyon, which has some sort of like reliability properties. It separates the failure modes from your executor process from the failure modes of your data storage.
So getting off the heap and onto the stack might be a little bit beneficial, and maybe using
right. I mean, I guess
cryo to like
I don't know if it would be
better serialization.
Right.
Serialization off onto the stack maybe.
Mm-hmm.
But it's more about reuse across the cluster, like better distributed cache, I guess, maybe, if you want to like enter results to.
Right. So I mean, I think the coolest thing what it can do that no other systems can do is allow this avoid you to hit disk when you're writing a data set out, so that it can be, let's say, immediately read by another job. So it sort of depends how important that kind of thing is to your workload. I wouldn't say I've ran into a ton of workloads where that's a main need. So I think that's been part of our reason for not having proactively included it in CDH so far. But to the extent that that comes up, we probably include it in our platform. You have a question?
We've been having an issue that job manager registering. We're hoping to see that actually. So we have an insight about what is it pointing at. A typical Spark job for you.
So it's a block manager.
Deregistering.
Oh, block manager is re-registering. So I think that could be probably a lot of different things, unfortunately. Basically what happens is and each executor has something that's called a block manager, and the block manager is in charge of like all data the executor needs to store. So if you cache data, it'll store those blocks. If you do a shuffle, it'll keep track of the blocks that are on disk. And so the executor and by proxy the block manager are constantly heartbeating into the driver. If the driver doesn't get heartbeats for a long time, it'll tell the block manager to re-register. It'll say like something must be wrong. It'll send out a message. So it could be just that there are network issues, that somehow the ability to communicate between the executor and the driver is compromised.
Actually, we see that when the job is processing, if it's a long-term process, it does not heartbeat back. That's when we see this blocking, especially when the data set is humongous, can do a number of tasks.
Right, so it could be that it's stuck in a GC pause or something like that. I know that there's a timeout that you can increase. I forget the property name, but that might help you with it.
So I've had some issues with working with the ML in Python, and so as a debugging step, I'll try to recreate it in Scala and not have the issue. So are there special issues about working with Python that we should be aware of when debugging?
So the question is, are there special issues to be aware of when working with Python and debugging? I think there's probably 3 classes, or 3 things that sort of come to mind. One is, we do our best to ensure compatibility and, reliability between Python and Spark, but at some level there's code that's different between the two. So often, you can hit a bug in Python that doesn't exist in Scala. Another thing is you often hit like performance issues because you're trying to send data over the over a pipe in that way, and there's pickling kind of stuff. Last of all, because Python runs in your Python code runs in a separate process than the MLib code, you can run into the off-heap thing that we were talking about before. If that Python process is taking up a bunch of memory, then you need to account for that inside your Spark yarn memory overhead kind of stuff. Does that somewhat answer your question?
Similar to the issue that was being discussed, the typical phantom dimension joins that we have, like one huge table and a lot of reference data. To resolve that, we tried doing the broadcast-based joins,
Mm-hmm.
broadcasted the smaller tables, but that didn't seem to work. So is there anything that you're aware of, any limitation? We were not able to make it broadcast and we had issues.
So when you say you do a broadcast join, is this inside Spark SQL and you're like calling a broadcast join method, or you're collecting the data to the driver?
Right before we register the table, like use the RDD which has been broadcast,
Mm-hmm.
then register the table and use the SQL.
So do you know what kind of issues that you're hitting when you do that?
It really didn't broadcast. We were seeing that it was still shuffling.
Oh, it's still shuffling.
Yeah, it didn't really broadcast.
Oh, that's weird.
Probably we can do it right, maybe.
Yeah, so it sounds like it's a Spark SQL issue. Unfortunately, I'm not super familiar with the implementation details there.
Right. The thing is, there is no broadcast link like we have in Impala or anything with Spark SQL.
Mm-hmm.
We got it rolled outside of Spark, and then maybe that would have missed somewhere, like it's not really being broadcast.
Yeah, I'm not exactly sure. I would definitely ping the Spark user list and say, this is what I expected to be broadcasting, but it doesn't seem to be broadcasting. Then someone can help you on there.
Is there an easy way to monitor how much spilling is going on? And then the second question, you mentioned data frames. I'm just curious, are there performance implications of using data frames versus RDBs?
Right. So to answer the first question, the Spark Web UI will give you a bunch of insight into that. So for every task, it gives you metrics for both shuffle spill memory and shuffle spill disk. They're sort of misleading names. What shuffle spill memory means is it's the size of the data took up in memory before you do the spill. Shuffle spill disk is the size of the data once it's been serialized and written out. So yeah, that's super useful. The other question was, are there performance implications of using Spark SQL versus using Spark Core?
Data frames versus RDDs.
Data frames versus RDDs. There shouldn't be big performance implications. The first one that comes to mind is when you're using data frames, you execute something the process for coming up with the, it delegates down to the catalyst optimizer. So there's a sort of slightly more involved process between taking your logical plan and converting that into a physical plan. In practice, I'm not sure how much overhead that provides. In theory, with data frames, there should be some optimizations that we can do in the future. Condense objects and use really efficient data structures. But it should be pretty similar.
Thank you.
Is there a way to track actually the metrics of the completed jobs? Because what I see is, Spark Web UI, as soon as the job completes, the context gets destroyed and even the UI goes off. Is there a way that we can go and look for the metrics of the completed jobs?
Yeah, so are you familiar with the Spark history server? Basically, there's this separate history server you can set up, and as Spark runs, it writes out metrics and stuff like that to a file on HDFS. And then you should be able to click around and browse completed applications inside the history server.
Okay, so will that have a specific UI similar to the Spark Web UI?
Yeah, it's like you almost couldn't tell the difference between the history server UI and the regular Spark Web UI.
Isn't data frame still the Spark streaming? What was some of the least talked about it? So is that still applied to the entire Spark ecosystem?
So the question was, are data frames only for Spark streaming? No, so you should be able to, so data frames are still sort of an alpha part of Spark, sort of came out of Spark SQL, but no, they're for batch as well as streaming.
It's the new schema RDB.
Exactly. Any other questions? Cool. All right. Well, thanks a lot for having me.